When Nader gave you a very nice talk this morning about practical issues in electromagnetism these days, my talk is more focused on basic theoretical aspects of classical electrodynamics. And in particular, I like to talk about Maxwell's macroscopic equations, the energy and momentum postulates in classical electrodynamics, the Lorentz law of force, and how all these things come together in terms of consistency with conservation laws, conservation of energy, momentum, angular momentum, and also in terms of consistency with the special theory of relativity. And even though these equations have been known since Maxwell put them together in the 1860s, early 1860s, there are still problems in terms of consistency with conservation laws. And as I will mention, the question of momentum of light in material media is still very controversial. So one of the things that I like to point out today is a connection between momentum in electrodynamics, classical electrodynamics, and the Doppler shift. And eventually you will see that this is a quantum issue, because when we use Doppler shift to calculate the force of light on material media, we rely on the fact that each photon has energy h bar omega. And this is a fundamentally quantum feature of the Doppler shift and the energy of the photons, which I'll show that Doppler shift leads to exactly the same result as classical electrodynamics. So that would be an interesting connection between quantum optics and classical electrodynamics. I have broken my talk into two parts. If there are lots of questions and we don't get through the first part, then I'll just stop at the end of the first part. If not, I'll have a few more slides in the second part. So you all know that light or electromagnetic waves consist of electric field and magnetic field, and that they propagate in vacuum with the speed of light c. They propagate in material media. You also know that light carries energy. But many people, at least in graduate school, don't appreciate that light also carries momentum and angular momentum. So let me give you a very elementary example of how electromagnetic momentum comes about. This is a thought experiment due to Einstein, Albert Einstein, in the early 1900s. So he said, suppose we have a box, empty box, sitting on a frictionless rail, and we have, do we have a stick here or a pointer? Here's one. I found it. Thanks. Because we have a blob of material on the left-hand side, and at some point in time, a pulse of light gets out of this. And this pulse of light has energy E, which you can write it as mc squared, and to call m the mass of that light pulse. Yes? No, this is old-fashioned, my style.
That doesn't have a cell phone either.
So this is the mass of the light pulse equivalent to its energy. And let's say that the light has a momentum p. And at this point, we don't know what that momentum is. But this is like a bullet of light coming out, and energy is known, but there is some momentum associated with that. The box has length L. The mass of the box is m, and Einstein assumes that m is very large compared to this m. So he can make this argument more simply. Now, as soon as the pulse leaves the left-hand side, the backlash makes the box move backward. So the box will start rolling to the left with the same momentum p in the opposite direction, until the pulse reaches the right-hand side, gets absorbed here. This is a perfect absorber, so the entire pulse gets absorbed, and at that point, the momentum goes back into the box stops. So in this process, the box gets displaced. It moves slightly to the left. But Einstein said that there is no external force acting on this box. There's no friction, there's no force that's coming from the outside, and therefore the center of mass of the whole system cannot have moved. So this mass moves slightly to the left, this mass moves slightly to the right, but the center of mass cannot have shifted. So here's the time of flight, the length of the box divided by the speed of light c in vacuum. Remember, inside the box is empty, so this is just c in vacuum. The recoil velocity is minus p. That's the momentum that's given to the box divided by the mass of the box. So that's the velocity. So the box displacement is its velocity times the time. That's how much the box is displaced. So the center of mass displacement then is the mass of the light pulse, E over c squared from here. It's displaced by L. It comes to the right. The mass of the box is m. It's displaced by this much. And so the total displacement must be equal to 0. Very simple argument. The center of mass cannot have moved. And now if you eliminate L and C and M from this equation, what you find is that the momentum must be E over C. So very simple. The energy divided by the speed of light in vacuum, that's the momentum of the pulse. So light carries momentum, linear momentum in this case. And in vacuum, that momentum is given by the energy divided by C. So that's how we know that light carries momentum. And of course, this was already known to Maxwell. Remember that Maxwell died in 1879, and that's the year that Einstein was born. So Maxwell couldn't possibly have known of this thought experiment. But he knew from electrodynamic theory that he developed that light must have momentum. And his estimate of the momentum was exactly the same as Einstein's. So here's another way to look at the interaction of light with material media to take the momentum into account. Suppose you have a mirror. It's a perfect mirror, 100% reflector, and it has mass m0, and it's sitting way outside the gravitational field of the Earth. No friction, no gravity, nothing. It's way outside. And a pulse of light is shining on this mirror. The pulse of light has this much energy, and energy is equal to n. That's the number of photons. H is Planck's constant, and F is the frequency of the photons. So n times HF is the energy of the light pulse that is shining on the mirror. And what happens is that pulse is going to get reflected 100%. Because the mirror is perfect, there's no absorption. So now the light is going the other way, and so its momentum is reversed, right? Momentum is energy divided by C. After reflection, the momentum is reversed, and the change of momentum must be transferred to the mirror because momentum is constant. Of the whole system must be constant. So this mirror must start moving to the right. And so what we have now is mirror moving to the right with velocity v. It has momentum, which is its mass times velocity. It has kinetic energy, 1/2 mv squared. And I'm assuming that v is small enough that we can use this non-relativistic formulas for momentum and energy. And many people at first said that, well, this cannot be because here we have kinetic energy. And if the pulse gets reflected, and it's 100% reflector, so no energy is lost. And therefore, we cannot give any energy to the mirror. But that argument is faulty because they did not take into account the Doppler shift. So when the light gets reflected, its frequency will not be exactly the same. Frequency is f prime, the same number of photons because no photons are absorbed, but the frequency is f prime. And therefore, energy of the light pulse is different. It's E prime. And if the light is redshifted, so the frequency comes down, this energy is lower than the initial energy, and the difference goes into the kinetic energy. So the kinetic energy comes from the Doppler shift, the redshift of the incident pulse. Incidentally, if you write the laws of conservation of energy and momentum for this system, so energy before is this much, energy afterward is the energy of the light plus the energy of the mirror. Momentum before is this much. Momentum afterward is this much with a minus sign because it's going the other way, plus this one. So these things should be equal. Before and after, both energy and momentum should be the same. And if you write these equations, what you find is an expression for the Doppler shift. This is a nice way to get the formula for the Doppler shift by just writing the balance of energy and momentum in this system.
So the sign of the Doppler shift is, where is the observer? Is the observer on the mirror, or is the observer on the photon, or is the observer somewhere else?
Okay, the observer is sitting in a system in which this mirror is initially stationary. So initially the mirror is stationary, the source of light is stationary, and this is the frequency of the photon that is emitted. Afterward, the observer is still stationary, but the mirror is moving with this velocity, and the photons that are reflected have been redshifted.
The observer sees them as redshifted.
The observer sees them as redshifted.
Okay, yes. All right.
Okay. So now here's another interesting point. If you look at this expression for energy, 1/2 mv squared, I can write it also in this way. I can divide and multiply by m0, so the energy is m0v squared divided by 2m0. Now the numerator mv is the same as the momentum. So I have the momentum here, which is a finite value, the momentum that's transferred to the mirror. But now in the denominator we have m0. Now if m0 is very large, you see that this energy can become very small. You can transfer the finite momentum to this mirror. That would be this. But the energy that you transfer to the mirror could be insignificant if the mass is large enough. So it's possible to transfer momentum to the mirror without transferring much energy. And that's why normally we do not notice the Doppler shift, because normally the mass of the mirror is much larger than the mass of the photons, and therefore the energy, the kinetic energy that's given to the mirror is insignificant. The Doppler shift is insignificant, but there's a significant amount of momentum that is transferred to the mirror. This is important, but this term could become zero. In fact, if you brought this mirror down to Earth and connected it to the floor, then the effective mass of the mirror would be the original mass plus the mass of the Earth. Now, a mirror that's tied down to the floor has essentially the mass of the Earth, which is huge, and therefore there's no energy, no significant amount of energy transferred by the light or from the light to the mirror. If you want to do it more accurately, write the equations relativistically. So this is the relativistic formula for momentum, and this is the relativistic formula for energy, mc squared over the square root. Now you can write again the equations of the balance of energy and momentum, and this time you get the relativistic formula for the Doppler shift. You get the exact relativistic formula for the Doppler shift. You can get it from relativity theory, but you can also get it from the energy and momentum balance equations. Now this is a simple example of how light exchanges energy and momentum with a mirror. But now let me turn this argument upside down. Let me look at it in a completely different way. Suppose I know the formula for the Doppler shift. This is something that we can get from special relativity. You have a mirror, light shines on it, and if the mirror has a velocity, you can calculate the Doppler shift. So now we know how much energy is transferred to the mirror. The mirror is initially stationary, then it starts moving, so the final velocity is Vf. So this is the formula for the Doppler shift. Because I'm assuming a large mass for the mirror, I can use the non-relativistic formula. So this is the new frequency compared to the old frequency, the incident frequency and the reflected frequency. And you see that there's a factor of 2 here, 2 times V. And 2 is because if the observer is stationary, looking at the source of light in this mirror, so the source of light, which is somewhere here, has an image, a virtual image in the mirror somewhere here. Now if the mirror starts moving with this velocity, then the source appears to be moving away from us at twice the velocity of the mirror. And that's why we have a factor of 2 here. because the source, the image of the source in the mirror appears to be moving away at twice the velocity of the mirror. But in any case, that's a well-known formula for the Doppler shift of the light reflected from a mirror that has a velocity v. But what's the effective velocity here? Remember, the mirror at first is stationary, but eventually it has this velocity. So the average velocity is 1/2 of the final velocity. Because the photons that hit the mirror at first, they see essentially zero velocity. But towards the end, the mirror has a velocity vf, and so the average velocity seen by the photons is 1/2 of the final velocity. So now if I'm going to use this formula, the change in the energy of each photon on average is going to be hf times this thing, but the velocity is 1/2 of the final velocity. So that would be this. I'm writing vf for v final. These are the same thing. So this is the amount of energy that the photons have lost in the process of reflection. Nothing has been absorbed. The mirror is perfect, no absorption, but just Doppler shift causes this much reduction in the energy of the photon. And here's the kinetic energy of the mirror, 1/2 mv squared, which must be equal to the shift in the energy of the photons. So these two things are equal now. And you can see that I can eliminate 1v from both sides. And on the left side, we're left with mv. So the momentum acquired by the mirror is now given by 2h f over c. So each photon gets reflected. Remember, the energy is hf. Energy divided by c is the momentum. We get twice the momentum to the mirror because one unit of momentum is coming in, the second unit is coming back. Therefore, 2 units are given to the mirror. So we get this formula for the momentum transfer to the photon. And this is a Doppler shift argument. This is not coming from the electromagnetic theory. This is coming from the Doppler shift. Now I have a much better example of Doppler shift in a few minutes, but this is just the first elementary example that shows how things work. Because this V gets canceled out from the two sides of the equation. We write the balance of energy equation, V gets canceled out, we end up with the momentum expression. Now I mentioned that Maxwell had his own way of looking at this problem and figuring out that light has momentum. Here's how Maxwell looked at it. If you have a particle of charge q moving with velocity v in the presence of electric field E and magnetic field B, there's a force on this charge, and that force is known as the Lorentz force. Even though Lorentz introduced the formula in 1892, that's 13 years after Maxwell had died, but Maxwell already knew this. He had this in his book. It's just in a different context, in the context of Faraday's law, that he had introduced this equation. But this equation was known to Maxwell, the force of light on charged particles. Now, if instead of a single point particle we have a distribution of charge, then this formula can be written in the following way. The force becomes force density. That's force per unit volume. Force density. QE becomes rho E. Rho is the charge density, that amount of charge, electric charge per unit volume. So QE becomes rho E, but now we are talking about force per unit volume. QV is charge times velocity. That's the current. So current density is J. J cross B is the second half of the expression for force, electromagnetic force. So this is the same equation as the one we had for the charged particle. And of course here in vacuum we know that B is related to the H field, and mu naught is the permeability of free space. That's just the constant in the SI system of units. But now let's see how Maxwell used this formula to understand the momentum of light. So his argument goes like this. Suppose I have a perfect conductor. Perfect conductor is is a perfect mirror in electromagnetics, for electromagnetic waves. A plane wave is coming down at normal incidence onto the surface. The light wave has electric field E and the magnetic field H. Now, when the light gets reflected from the surface, the electric field flips. The reflection coefficient of a perfect conductor is -1, so the electric field has the opposite direction. So that means on the surface, there is no net electric field. But because the direction of propagation has reversed and the direction of electric field has also reversed, the magnetic field cannot reverse. So the magnetic field of the two beams are in the same direction. That means that on the surface, we have twice the magnetic field of each plane wave. And now the magnetic field on the surface is 2H, but just beneath the surface, the magnetic field is 0, because magnetic field cannot penetrate a perfect conductor. So there is a discontinuity in the magnetic field. Maxwell's boundary conditions tell us that that discontinuity is exactly equal to the surface current. So there's a surface current, J sub S, that is flowing on the surface of the mirror, and the magnitude of Js is exactly 2H, which is the field, this magnetic field discontinuity. This one minus the field beneath the surface, which is 0. So now this, if you go back to the previous formula, we don't have any charges here, so the first term is not relevant. But the second term, we have a J, which is the current, surface current, and we have a B field. B is just mu naught H. So the product, cross product of J and B gives us the force density on the surface of the mirror. So from Maxwell's equations, we can solve for the plane wave, and we find that the ratio of E to H is given by the impedance of free space. This is the formula for the speed of light in vacuum. J sub S, the surface current, is twice the magnetic field. And therefore, using the Lorentz force equation, we get the current cross the magnetic field. That's the force per unit area. There's a factor of 1/2 here, and that's because the magnetic field that acts on the surface current is the average magnetic field between above and just beneath the surface. And so this is whatever it is, 2H times mu naught, but beneath the surface is 0, so the average gives us 1/2 of that field. And so if you put those formulas in this expression, you get the Lorentz force density to be either mu naught H squared or epsilon naught E squared. These are identical. And so that's the formula for the force density on the surface of the mirror. And of course, the energy is given by E cross H in the beam. And if you assume that there is a momentum associated with the light that is given by Poynting vector divided by c squared, then you see that the change of momentum, light has momentum coming down, after reflection has momentum going up. That change of momentum must account for this force. And because there's a force at the surface, there must be a momentum in the light. So that's how Maxwell knew that there is momentum in the light in vacuum, because reflection produces a force on the surface, and that force must be due to the momentum of the light, or change of momentum of the light. Yes?
Masud, I understand the argument for Lorentz force ending up with mu naught H squared.
Yes.
And because at the surface, the amplitude of the magnetic field is 2 times the incident.
Yes.
That's fine. The next equal sign, epsilon naught times E squared.
Yes.
Since it's E squared. All right, never mind.
Yeah, it comes from here.
Yeah.
Yeah.
Okay. So I was thinking about the fact that the electric field changes sign, and then if you took the average of that, then
No, it's a square.
But it's E squared, so then that's how you get out of it. Okay.
Right. And this is the E of each beam, either in the incident beam or the reflected beam. So it's only at the surface that the E field is 0. As you go back, the interference gives you 2E0, 0, 2E0, 0 as you go back. Anyway, so this is another way to convince yourself that light carries momentum, because after reflection, there is a force on the surface, and that force must be due to the change in the momentum of the incoming light. And you get exactly the same answer as you get from Einstein thought experiment. All right, so now here's another interesting argument. Suppose you have a piece of glass, dielectric material of some refractive index n, and there's a mirror that is sitting back here at some gap between them d, and the mirror has a reflection coefficient. This is the Fresnel reflection coefficient, amplitude and phase for the mirror. A good mirror, a perfect mirror, has rho equal to 1, but it could have a phase. A metallic mirror typically has a phase close to 180 degrees. A dielectric mirror, if you make it out of high-low refractive index layers, if those layers are exactly quarter wave thick, will have a phase of 180 degrees. But you can also make a dielectric mirror that has any phase that you want. You can make a dielectric mirror whose layer thicknesses are not exactly a quarter wave, and then you can change the value of psi to be anything between 0 and 180 degrees, while keeping rho as close to 1 as you may desire. Now, a pulse of light is arriving here. The pulse of light has energy E, duration tau, frequency, center frequency omega 0. And I'm assuming that the front facet of this dielectric is anti-reflection coated, so there is no reflection from the front surface, just to simplify the matters. Light comes in, everything goes through, but then there is reflection from this surface, there is reflection from the mirror, there is interference among all the various reflected beams, and eventually the light comes back and goes the other way. If the mirror is perfect, all of the light eventually bounces back and goes through. So I want to look at this system and find out how much force, how much pressure the light exerts on the mirror. But now things are different because we have this piece of glass here, whereas previously we were just looking at just the mirror in vacuum. And I want to do this in two different ways. First, I want to keep the mirror stationary. First, I want to get the mirror to move at some velocity so that there is Doppler shift. If the mirror moves, there will be Doppler shift in the reflected light. And use the Doppler argument to find out the force on the mirror. And the second time, I like to just keep the mirror stationary and look at the field here and find out, like Maxwell's idea, how much force is exerted on the mirror. So the Doppler shift is due to the motion of the mirror. This Doppler shift can be measured. So let me give you just a simple example of how to measure the Doppler shift. Suppose you take a mirror and put it behind a prism. I use a prism because the front facet is slanted, and if the light comes at this angle, there is no reflection. So you don't need to put anti-reflection coating on the mirror. So the fraction of the light gets reflected, the rest goes through, interacts with the mirror, but on the way back, there's a fraction of the light that's reflected this way. So now you have to worry about this, and if you put a black surface here, or just grind the surface, scratch it to get that light scattered out, one way or the other, you get rid of this light. So now it's just like having anti-reflection coating on the mirror. Then we build a Michelson interferometer here. So the light source is a laser. We split it into two beams. This is a reference mirror. You interfere the light coming back from the reference mirror from the light coming back from the vibrating mirror. This mirror is now sitting on a piezo actuator and it's vibrating at some frequency. So the gap is now a function of time because the mirror is moving. So you interfere the reflected light from this mirror with the reflected light from that mirror, and at your detector, the signal that you detect tells you what the phase is, the phase of the light reflected from this mirror. And that phase is now a function of time because the mirror is vibrating, and if you differentiate that phase with respect to time, you get the Doppler shift. So at each instant of time, you can calculate the Doppler shift because you know the phase as a function of time. But now the Doppler shift depends on this refractive index. It also depends on the gap. At each instant of time, the gap is different because the mirror is oscillating. And so when you calculate the Doppler shift, it is not just related to the velocity of the mirror. It is related to the refractive index n, and it's related to the gap d. But now going back to the original experiment, I want to find out the Doppler shift of the reflected light. So at this point, which is my reference point, z equal to 0, the light has an amplitude and a phase. So if you set the mirror to a fixed position, so that D is a constant, you can easily calculate the reflected amplitude and phase of the light. This you do by simple electromagnetic theory. You look at the light reflected from here, the fraction of it is transmitted, getting reflected with this amplitude and phase. At this point there's another transmission, then you add them up and you write consistency equations. That's very simple, it's straightforward optics problem, and you can find the amplitude and phase of the reflected light when D is some constant value. So when you do this, you get this formula. So this is R e to the I phi, which is the amplitude and phase of the reflected light. And now you see that it's related to the refractive index of the glass. It's related to the amplitude of the reflection coefficient from the mirror, the phase of the reflection coefficient, the gap D, the wavelength of the light. So this formula gives us the dependence of phi on the gap. Now I make the gap a function of time. In other words, I let the mirror move with some velocity v. So the initial gap is d0. It moves with velocity v, so the gap is changing with time. Now if the gap is changing with time, that means that the phi, the phase, is now a function of time, because d is a function of time. And the derivative of that is the Doppler shift. So by differentiating phi with respect to time, I get the Doppler shift. And this is the formula for the Doppler shift. It's a couple of pages of algebra that you have to do, but conceptually it's straightforward. You go from the phase to the Doppler shift. And now you see that the Doppler shift depends on the frequency of the light, on the refractive index of the glass, on the velocity of the mirror, and on the phase psi naught. And the psi naught is the phase of the mirror plus the round trip phase acquired by the beam of light in going through the gap. 4 pi d over lambda, because it's twice the length of the gap that is traversed by the beam. So you see that psi and d appear together in this formula. The only thing that matters is the combination of this phase, which is due to the mirror, and this phase, which is due to the gap. So now we have a nice expression for the Doppler shift. Now you have to remember that when I did the calculation of phase at first, d was constant. But then I started to move the mirror, so d became a function of time. You cannot do this when the mirror is moving too fast. The mirror has to move slowly, because if it moves too fast, then there is not enough time for the multiple reflections in the gap to build up. This formula for phi assumes that the light has bounced back several times and it has reached the steady state. And that requires the mirror to move slowly. If the mirror moves too fast, the formula is not valid. But in this case, when we talk about slowly, we mean 100 kilometers per second. Compared to the speed of light, it must be slow. But for this application, I just need the mirror to move at microns per year. And therefore, it's a perfect approximation in the context of radiation pressure. All right, so now we have a formula for the Doppler shift. And then we go back and write the conservation of energy. So here's the conservation of energy equation. Each photon has energy h bar omega naught in the beginning. The photon that is coming toward this system has energy h bar omega before it hits the mirror. Afterward, the mirror has a velocity v, so it has a kinetic energy. That's the kinetic energy of the mirror. And this is the kinetic energy, this is the energy of the photon after reflection. It is the Doppler shifted frequency times h bar. This is the same formula I had on the previous page. So Doppler shifted frequency times h bar. And now you see that h bar omega cancels out. One of the velocities drops out, and I'm left with this formula. Sorry. I'm left with this formula that says mv, the momentum of the mirror, is given by this formula. But using conservation of energy, I now have an expression for the momentum of the mirror. And now you see that if the phase is 180 degrees, then cosine of 180 divided by 2 is 0. The formula will give me this, 2n h bar omega over c. But if the phase is 0, then this cosine squared is equal to 1, and the formula gives me this. So depending on the phase, psi 0, I'm going to get either this much momentum or this much momentum. So either n times more than the momentum that I get in vacuum, or n times less than the momentum I get in vacuum. And all by changing the phase. And this phase, psi 0, recall that it is the sum of psi and 4 pi d over lambda naught. So either you use a mirror that has a different phase, a multi-layer stack, for example, that you have designed it for a particular phase, or you just change the gap. The gap at the instant that you're looking at the radiation pressure on the mirror. So either way, depending on the phase, you're going to get either this much momentum or that much momentum. Now, as I said, this question of photon momentum inside the dielectric has been controversial. For about 100 years, people have argued as to what is the momentum of the photon when the photon goes inside the dielectric. In vacuum, there is no controversy. Everybody knows it's h bar omega over c. But once the light gets into the material media, inside the dielectric material, for example, then there are two schools of thought. One of them is due to Hermann Minkowski, and the other one is due to Max Abraham. And both papers of these two men were published in 1908. So according to Abraham, the photon inside the dielectric has momentum h bar omega over n times c, divided by the refractive index. According to Minkowski, it's n times h bar omega over c. And for the past 100 years, people have argued which one is correct. They have done experiments, and they have found some experiments give them this, and some experiments give them that. And theoreticians have tried their hand at this, and some people agree with Minkowski, some people agree with Abraham. And one of the experiments that has been heavily cited in support of Minkowski's formula has been an experiment done in the 1950s and then repeated again in the 1970s on a submerged mirror. They put a mirror underwater or under some other liquid, measure the pressure on it, and in the experiment they always find that Minkowski is right. The photon momentum must be n times h bar omega over c. But this experiment that I just showed you a mirror behind the dielectric is in fact the same thing. It's a submerged mirror. If you set the gap equal to 0, it will be a submerged mirror. And now I showed you that the momentum that the mirror picks could be either this one or that one. This is the Minkowski momentum. This is the Abraham momentum. And so what people have not looked at before has been the phase of the mirror. The phase of the mirror has always been 180 degrees. And if you use a 180 degree phase for the mirror, you always get the Minkowski answer. But if you use a different mirror, and no one has done this experiment, this is an experiment that remains to be done. If you change the phase of the mirror, then you get the Abraham value. So now I have worked on this problem for about 8 years now. And I have argued that the momentum of the photon inside the dielectric is neither of these. It's neither Abraham's nor Minkowski's. I have argued that the momentum of the photon inside the dielectric is in fact exactly halfway between the two. If you average these two values, you get the correct value of the momentum of the photon inside the dielectric. And this experiment of reflection from a mirror I have used in the past to argue that the photon momentum is in fact halfway in between. And the amount of momentum that is transferred to the mirror depends on whether your phase shift is 180 degrees or 0. In fact, if the phase shift is anywhere between 0 and 180 degrees, which you can make a mirror that has that phase shift, you are going to get a continuum of values for the radiation pressure. Anything between these two extremes is possible. So what happens is that the light gets reflected from the mirror, and there is interference between the incident light and the reflected light. In the interference region, which is right in front of the mirror, there is a force exerted on the liquid itself, or on the dielectric in this case. And that force transfers some momentum to the liquid. And what the mirror sees is just part of the momentum, not all of it. Part of the momentum is given to the mirror, part of it is given to the liquid. The net momentum is the momentum of the photon. But how much of it is given to the mirror depends on a lot of factors, on the refractive index and also on the phase of the mirror. But the argument that I have used in the past has always relied on the Lorentz force. But now this is the first time that I use the Doppler shift. And the Doppler shift argument gives exactly the same answer as the Lorentz force. And the Lorentz force argument goes like this. So here's the incident pulse. It has this much energy. The electric field is squared, duration, impedance of free space. And for a single photon, the energy is h bar omega. So that's the formula that relates the electric field intensity to the h bar omega of the photon. And then you can use the standard electromagnetic calculations to find the electric field in the gap. G stands for the gap. The E field in the gap is given by this formula, which is related to the phase of the light reflected from the glass, phase of the mirror, and when you put this value for electric field in this equation, then the mirror momentum is exactly the one that I got from the Doppler shift. So whether I use the Lorentz formula or use the Doppler shift, I get exactly the same answer. So that's the argument in favor of the formula for the momentum of light inside dielectric media made through the agency of the Doppler shift. But now let me tell you something more general about classical electrodynamics. What are the fundamental tenets of the classical theory? People refer to this as Maxwell's theory of electrodynamics, but truly we should, as Einstein recommended, we should refer to this as Maxwell Lorentz, because these are the two people who made the most contribution to the classical theory. And the Lorentz is the Hendrik Lorentz, not the Danish Lorentz. These are Maxwell's equations. And I have written the macroscopic equations of Maxwell. I have D here and B here. And the four equations of Maxwell can be summarized in this way. When they asked Heinrich Hertz, what was Maxwell's theory of electrodynamics, he said Maxwell's theory is Maxwell's equations. In other words, there's nothing else there. But I think he was wrong. There is a lot more to classical electrodynamics than just Maxwell's equations. So my first argument is that when you use Maxwell's equations, you have a choice between the microscopic equations and the macroscopic equation. In the microscopic equations, you do not have D and H. Everything is written in terms of the E field and the B field, which is something that the physicists love, the engineers abhor, because engineers love the H field. But I am arguing in favor of the engineers, that the D field and the H field are essential, and Nader agrees with me, because without the D field, he wouldn't have a career. Neither would I, by the way. Anyway, so these are the macroscopic equations. And why was Heinrich Hertz wrong, or at least partially correct? Because there is more to electrodynamics than just Maxwell's equations. And we will see what else has to be taken into account. But for now, let me just tell you that the D field in general is given by epsilon naught E plus P. P is the polarization density. Epsilon naught is the permittivity of free space. And in general, you don't need to go beyond this formula. P does not have to be linear, does not with the electric field. In fact, does not even have to depend on the electric field. But people usually write P proportional to the electric field. Susceptibility is the proportionality constant. Then they combine them into this formula that gives us the epsilon, the permittivity or the dielectric constant of the material. That's fine, but that's just true for a subclass of materials that happen to be linear in the electric field. Polarization is proportional to the electric field. So in general, the red formula is the formula to use in Maxwell's equations. And similar one exists for the B field. The B field, which is the magnetic induction, is mu naught H, H being the magnetic field, and M being the magnetization. So again, if you have a linear material, linear in the sense that magnetization is proportional to the H field, you get this formula for permeability of the material. But again, the red formula is the more general formula that I like to use for this discussion. So now if you take Maxwell's macroscopic equations, you find that there are 4 sources of electromagnetic field. There is free charge, free current, polarization, and magnetization. These are the material parts of the Maxwell's equations. And then there are fields, E and H, electric field and magnetic field. And of course, if you want to get B and D, you go to these formulas. B and D are composite fields. They have material in them and they have fields in them. So there are 4 sources and there are 2 basic fields, the E field and the H field in Maxwell's theory. And all the Maxwell's equations tell us is the relationship between the fields and the sources. If you know the sources, you can calculate the fields. If you know rho, J, P, and M, you can calculate E and H. Yes? Yes. Yes.
Does polarization
yes.
magnetization represent those bounded?
Exactly. Exactly. In fact, I have a slide in a couple of minutes that shows that. But you can express B in terms of bound charge and bound current. Minus divergence of P is the bound charge density. dP dt is the bound current density. You can also write M as bound current. There is no charge associated with M, just current, and that would be the curl of M. So now if you replace in these equations P and M with their time derivative and divergence and curl, then you have only free charge and bound charge, free current and bound current, but nothing else. Yeah, so it's the same thing as bound charge and current that we call P and M here. Yes. No, I won't talk about Lorentz transformation here.
But then the question would be that if you like E and H, are these also comparing under the Lorentz transformation?
Yeah, good question. E and B can be Lorentz transformed from one reference frame to another. D and A, because they form a second rank tensor, E and B. D and H also form a second rank tensor, and you can transform them from one frame to another, one inertial frame to another. But E and H do not. E and H do not form a Lorentz transformable entity. Yes.
Maxwell's equation will vary under the Lorentz.
Yes, the Maxwell's equations would be invariant because you can convert everything like P and M into bound charge and bound current. And bound charge and bound current, and of course free charge and free current, together they form a 4 vector. And you can transform that 4 vector from one reference frame to another. And so in one frame, you can calculate the total charge and total current, and then transform them to another frame. And in the other frame, you can calculate E and B in terms of the charges and currents. And that E and B is exactly transformed from E and B in the other frame. Yeah, so you can do that. What you cannot do is Lorentz transform energy and momentum from one frame to another. And that's just because these are electromagnetic energy and momentum. There's also material energy and momentum. When you combine them together, electromagnetic energy momentum plus material energy momentum, then that forms a Lorentz transformable entity. It's a second-rank tensor again that you can transform. So these are the points that I want to make about Maxwell's macroscopic equations. One, these are mathematically exact. Now again, people don't tell you that. At least Jackson doesn't tell you that. Landau and Lifshitz don't tell you that. They all tell you that the microscopic equations are the exact ones. The microscopic equations, by the way, are the ones that you get if you set P equal to 0 and M equal to 0. If there's no P and M, you just have rho and J, you have microscopic equations. And they say those are fundamental. And they say, well, you have to do some sort of averaging over the dipoles to get P, some sort of averaging over magnetic dipoles to get M. And it looks like macroscopic equations are some sort of dirty, averaged over thing that you really shouldn't take too seriously. But I say that's just a practical way to get values for P and M. But in principle, these equations are mathematical equations. And P is just a function of space and time. Think of it as a continuous differentiable function of space and time. Think of M as a continuous differentiable function of space and time. Then these equations are mathematically exact. There's no approximation here. There's no small volume over which you have to average electric dipoles and magnetic dipoles to get these equations. Mathematically, these are exact. If anything, it's nature that is an approximation to these equations. The equations themselves are perfect. They are exact, they're self-consistent, and they're consistent with conservation laws, and they're consistent with special relativity. So no small-scale averaging required if you think of these as just differentiable continuous functions of space and time. But I also want to argue that these are more fundamental than the microscopic equations. The microscopic equations do not have P and M in them. These ones do, so they are more general, but it's not enough to write this bound charge and bound current and reduce them to the microscopic equations. Of course, you can do that if all there was to the electromagnetic theory was Maxwell's equations. Within the context of the Maxwell's equations, of course, you can replace P here with dP dt. You can introduce curl of M in the equations and get rid of the P and M. But the problem is that there is more to the electrodynamic theory than just Maxwell's equations, contrary to what Hertz had said. There is still the pointing vector, there is still the momentum, there is still the Lorentz force. And when you take those into account, it is not enough to reduce these things to bound charge and bound current. You have to treat them separately. Yes?
Actually, how about also constitutive relation? Of course, you embed them in the expression, but that also required.
Well, the constitutive relation, for example, would be here. You know, what is epsilon? But these are just special cases. These are when you have linear material or nonlinear material. But what I'm saying is that ignore the constitutive relations. Just assume that P and M are arbitrary functions of space and time. What drives them? You know, usually it's electric field that drives P. It's a magnetic field that drives M. But imagine an ant or an army of ants sitting there. Each one of them has a dipole in his hand. I don't know if ants have sex, his or her hand. And they're rotating those dipoles, you know, making them longer and shorter. And so the driving force for changing P and M does not have to be the electric field or magnetic field. It could be some mechanical force, like ants doing it based on a program. Somebody wrote a program and told ants, you know, do this. At a certain time, rotate the dipole or elongate the dipole. They are, P and M are sources of the fields, but they do not have to respond to the fields. They can, in the sense that the constitutive relations require them, they can be just driven by something else, like a mechanical source. If I put electrons, if I glue electrons on this stick, okay, I have a charged wire. Now, if I take this stick and run with it, then I'm creating a current, because that charge is moving. But that current is driven by mechanical force that I exert on this stick. It has nothing to do with any electric field that may be acting on the charges at that time. There could be electric field here, there could be magnetic field. When I move this stick, it radiates. If I accelerate it, it radiates. And it produces electric field, produces magnetic field, and those fields could act on these charges. But as long as I make sure that the force that I exert on this balances the force of the E field and the H field, so that I get this thing to move at the velocity that I want it to move, I still have a current. I still have a source of radiation. But there is no need for constitutive relations in that case, because some other force is controlling the current. And the same thing can be said about P and M and rho and J. The way they change in space and time could be separated from their effects. And their effect is the fields that they radiate. And that's what Maxwell's equations tell us. If I give Maxwell's equations rho, J, P, and M, then they tell me what the radiated fields are. But the equations by themselves don't tell me how those sources are changing in time. Constitutive relations is one way to describe those sources as a function of space and time, but those are not the only ways. So that's part of the electrodynamic theory, classical theory, Maxwell's equations. What else do we have? We have energy postulate. Now, when you study electrodynamics, you learn that 4 years or 5 years after Maxwell died, his student, John Henry Poynting, discovered the Poynting theorem and told us what the electromagnetic energy is. But in fact, if you look at the way Poynting theorem is derived, you find that it's not unique. You don't have to define the rate of flow of electromagnetic energy as E cross H. You could define it as E cross B. In fact, when Feynman derives Poynting's theorem in his book, Undergraduate Lectures, he comes up with E cross B over mu naught, but he has B here, not H. I can derive Poynting theorem exactly the same way as Poynting did it, but instead of this, I would have D cross H or D cross B. So in fact, from the Poynting theorem, you cannot tell what the energy, electromagnetic energy is. Now it turns out that E cross H is the correct form of the rate of flow of electromagnetic energy per unit area per unit time. But it's not something that you derive from the Poynting theorem. It's something that you have to postulate. This cannot be derived in any other way. It has to be postulated. But once you postulate that, then you can turn things around and use Poynting theorem to write this expression. So Poynting theorem tells you that the rate of change of electromagnetic energy density is given by this expression. The electric field and the free charge and current, and the free current, they interact. If E dot J free is positive, electromagnetic energy is flowing into the current. If E dot J free is negative, electromagnetic energy is coming out, like in the case of an antenna or a radiator. E dot dd dt, that tells you how the energy goes into the electric field, and also how the electric field puts energy into the electric dipoles, or takes energy out of the electric dipole. This one tells you how the fields interact with the magnetic dipoles, take the energy in and out of magnetic dipoles. But the formula S equal to E cross H, Poynting vector being the product of E and H, is not something that you can derive from Maxwell's equations. Energy is not inherent to Maxwell's equations. It's a separate postulate. It's a new thing. So this has to be postulated. And of course, you can't arbitrarily postulate things. You have to make sure that energy is consistent with the conservation laws. And here, Poynting theorem tells you how to make sure that the definition of the Poynting vector is consistent with the conservation laws. If energy exchange between the fields and the media follows this formula, which is derived from Maxwell's equations after this other thing has been postulated, then energy will be conserved. And so that's an important thing to keep in mind. Then the next thing that you have to know is the momentum postulate. What is the momentum of the electromagnetic field? Again, it is something that you cannot derive from Maxwell's equations. It is not inherent in Maxwell's equations. It's not inherent in Poynting's theorem. And the fact that for 100 years people have been arguing over electromagnetic momentum is totally irrelevant and misleading in my opinion. Because there is nothing in classical electrodynamics that can tell us what the electromagnetic momentum is. It has to be postulated again. So that's why I said Heinrich Hertz was not right, because he just thought that Maxwell's theory is Maxwell's equations. No. Energy has to be postulated. Momentum has to be postulated. And it turns out that Max Abraham was right. His formula gives us the electromagnetic momentum density. And the formula for electromagnetic momentum density is just the Poynting vector divided by c squared. So if you have the Poynting vector at each point in space and time, r and t, divided by c squared, that gives you the electromagnetic momentum density. And now this is a completely general formula. It doesn't matter if you're in vacuum or inside material medium. It doesn't matter if that material medium is linear or nonlinear, if it's hysteretic or non-hysteretic, it's optically active or not, is it a gain medium or a lossy medium, is the field evanescent or not. Under all circumstances, this is a very general expression of electromagnetic momentum. Poynting vector divided by c squared gives us the density of the electromagnetic momentum. Once you have the electromagnetic momentum density, you also can find the angular momentum. The angular momentum is just r cross p, and p is this one. So electromagnetic angular momentum density is given by this formula, again under all circumstances. So these are two additional postulates. These are things that you cannot derive from Maxwell's equations. And finally, there is the Lorentz law of force. Now, we talked about the Lorentz law earlier. It turns out that if you take the Lorentz law and use it in conjunction with Maxwell's equations and in conjunction with these postulates, you are going to find that in certain cases, conservation of momentum is violated. So the total momentum of the system is not going to be conserved. And that's bad, because conservation of momentum is a fundamental tenet of physics, not just electrodynamics, but across the entire field of physics. You have momentum conservation, you have angular momentum conservation. Now Bill Shockley, who is very famous because he got a Nobel Prize for making the first transistor, sharing it with John Bardeen and Walter Brattain, he discovered in the early 1960s that in certain magnetic media, when light interacts with magnetic media, momentum is not conserved. And he referred to it as hidden momentum. There is momentum hidden inside magnetic material. And then a lot of people followed him in the 1970s and 80s and 90s. And even to this day, they still talk about hidden momentum, as though just calling it hidden momentum solves the problem. The problem is that momentum in classical electrodynamics is not conserved. You write the Lorentz law of force, you solve Maxwell's equations, light comes from vacuum, goes into the magnetic material, you know the force, you know the field, you calculate momentum before, you calculate momentum after, and you find that momentum is not conserved. So that's terrible. That's a bad thing. And just because Shockley called it hidden momentum, and just because Hermann Hauss, who was very famous, also called it hidden momentum, and they did hand waving and they said everything is okay because the momentum is hidden, that doesn't solve the problem. The problem is the Lorentz law. The Lorentz law is wrong. The Lorentz law is the thing that produces that hidden momentum. So at first, we just noticed that, at least we know that something is wrong. Either Maxwell's equations are wrong or the Lorentz law is wrong. But we are fortunate because there's a paper by Albert Einstein and Jacob Loeb in 1908. A lot of things happened in that year. Abraham and Minkowski both published their papers in that year too. But Einstein and Loeb also published a paper, and they gave us a formula for the force of the electromagnetic field on material media. And this is the formula. And it turns out that this formula is consistent with the conservation laws. if you use this formula instead of the Lorentz law, momentum will be conserved, angular momentum will be conserved, energy is already conserved because of the Poynting theorem, and so everything will be fine. Now there is a history as to why people have not followed Einstein and Loeb's lead, and the basic reason I think is that at the end of their paper they wrote the stress tensor for this force, and everybody has used the stress tensor since then, and they have found that the stress tensor has some problems associated with it. And even Einstein himself later in the 1916-17 time frame thought that Minkowski was right and his own stress tensor is wrong. The fact is that yes, his stress tensor is wrong, he and Loeb's stress tensor, but the force formula is in fact correct. I have shown that this formula conserves momentum, conserves angular momentum under all circumstances. You don't even have to specify the constitutive relations. Arbitrary P and M driven by ants as a function of space and time. Under the Einstein-Loeb formula, you get the correct conservation laws. You get the momentum to be conserved. Under Lorentz law, you don't. Not only that, I have recently found that the Lorentz law is also inconsistent with the special relativity. If you go from one reference frame to another under certain circumstances, special relativity is also violated. Whereas Einstein-Loeb formula does not have that problem. Special relativity is also consistent with the special relativity. So there are several arguments in favor of this formula. But what this formula says is that if you have the four sources, rho free, J free, P, and M, and if electromagnetic fields are around, this is how, at each point in space and time, you can calculate the energy, the force density. The force density is given by rho free times E, same as the Lorentz formula. J free cross mu naught H. Now here instead of B, we have mu naught H. So M is no longer in this formula, so only H acts on the free current to give us a force density. But the M part of this that used to be in the B field now shows up somewhere else. Electric dipoles respond to the gradient of the electric field, but also time dependence of the electric dipoles, dp dt, acts as a current. This is the bound current that you mentioned earlier. The bound current under mu naught H, the same mu naught H as here, gives us a force. Magnetic dipoles respond to the gradient of the magnetic field, but when magnetic dipoles alternate with time or change in time, then the cross dm dt with epsilon naught E gives us a force density. So this is the expression for the force density of Einstein and Loeb. And together with all the other things that I have mentioned, Poynting theorem, Abraham postulate, and Maxwell's equations, now we have a complete and consistent set of rules that give us the fields in terms of the sources, give us the force on the material media produced by the fields, gives us momentum and energy, and conservation laws are satisfied, and special relativity is satisfied. Yes?
We have the magnetic.
Yes.
We have matter.
We have matter.
Matter has its own laws and so on.
Yes.
So that one mechanics.
Yes.
So what is generalized Lorentz law does is when I have an interaction between these two systems.
Yes.
So even if you have polarization not provoked by the field,
Yes.
it's still there.
Exactly. So under all circumstances, it doesn't matter how material media are behaving. They could be driven by fields, they could be driven by ants, they could be driven by me or by mechanical forces of some sort. It doesn't matter. The exchange of force, the exchange of torque, the exchange of momentum is governed by the Einstein-Loeb formula. And there's a corollary to the Einstein-Loeb force because you have to take torque into account also, but torque is given by this formula. So torque is related to the angular momentum, force is related to the linear momentum, but these are the complete laws of electrodynamics, in addition to Maxwell's macroscopic equations. And again, I say macroscopic because the microscopic equations do not have P and M. If you do not have P and M, you wouldn't have these terms here, and therefore your theory is not complete. And these terms cannot be derived from the bound charge and bound current. They are derived from P and M directly. So that's a summary of the classical electrodynamics as we understand it today. Consistent with conservation laws, consistent with special relativity, and self-consistent. Yes. The question is, can we derive these postulates from the Lorentz law? Well, probably you can. If you apply the conservation laws, you can. Which means that this set of equations is not the minimum set of equations that you need. There's some level of redundancy here. But even the 4 Maxwell's equations are redundant. Right? The Maxwell's equations are not the minimum equations that you need. For example, you don't need 2 fields, E and B, that have 6 components. If you use the potentials, the scalar potential and vector potential with 4 components, you can describe the fields as well. So some degree of redundancy exists, both within the equations of Maxwell and among these postulates. But that's okay, because that makes life very simple. So now we know exactly what our postulates are, and we can go ahead and apply them. But whether I can derive the Abraham postulate from the Lorentz law, using generalized Lorentz law, using the conservation of momentum, it may be possible. I don't know how to do it. I haven't seen anyone do it, but it may be possible. You can start from the Lagrangian and Hamiltonian and derive these laws also. But that approach has been fraught with danger, because a lot of bad things come out when people start from the Hamiltonian or the Lagrangian for the fields. That's why I prefer to go this route. So now if you take an arbitrary system, take a system that has material media in it. If you want to describe them in terms of mu and epsilon, that's fine. If you want to describe them in terms of P and M, nonlinear media, that's fine. Light comes in, interacts with the media. Here you have evanescent field, reflected light, scattered light. So this is a closed system. Light and matter are interacting. And any kind of matter, any kind of electromagnetic field, if you not define the total Abraham momentum as the integral of Poynting vector over c squared over the entire volume of space. So this is the total electromagnetic momentum at each instant of time. The integral is over space, not over time. So you have the total electromagnetic momentum in the system. And then you have the total force in the system. I write Lorentz force, but I really mean Einstein-Loeb. This is the generalized Lorentz force. I didn't know about Einstein and Loeb until recently. Rodney Loudon pointed out to me that Einstein and Loeb have discovered this formula. But I arrived at the formula through the conservation laws, and I called it the generalized Lorentz law. That's why I write Lorentz law here, but Lorentz force here. But it's really Einstein-Loeb force. So if you integrate the force over the entire space, over all the material media, as a function of integral over space, you get a function of time. And now, the conservation of momentum is this. The force is minus dp dt. This is the electromagnetic momentum. This is the force on the material media. I can prove, under the most general circumstances, any distribution of matter, any distribution of field, I can prove that the total force is minus dp dt, which means that as a result of interaction between the fields and material media, if you lose electromagnetic momentum, for example, light is absorbed or light is reflected, therefore its momentum is reversed, that change in the momentum of the field, EM, electromagnetic field, appears as a force on the material media. And of course, the force pushes the material media and gives them momentum. And if the total electromagnetic momentum goes up as a result of this interaction, then the material media loses momentum. So the momentum comes out of the material media. So it can go both ways. Light can give momentum to the media, or media can give momentum to light. But in either case, the total momentum is conserved. Mechanical momentum, electromagnetic momentum. So people traditionally say that there's nothing new, interesting, puzzling about Maxwell's macroscopic equations. And I have argued that they are wrong. Macroscopic equations are not only beautiful, but they are more powerful and more general than the microscopic equations. People say that replace P with the bound charge density and with the bound current density. Replace M with the bound charge density, which is 0, because M doesn't have any electric charge, and the bound current density, which is curl of M. And then they say put them in Maxwell's equations, and you will see that the bound charge and current satisfy the continuity equation, the free charge and current satisfy the continuity equation. And you will also see that the total charge, which is the sum of free and bound, and the total current, which is the sum of free and bound, they form a 4-vector. Therefore, the Lorentz transformation that Nader asked about earlier applies to these bound charges. And so it seems that if you only look at Maxwell's equations, there is no reason to stick with the macroscopic ones. Microscopic ones are fine because everything can be reduced to charge and current. But that's only true if you only look at Maxwell's equations. As soon as you bring in the Poynting vector, momentum, angular momentum, force, then this is not sufficient. This is good enough to deal with the Maxwell's equations, but not good enough to deal with energy and momentum. In fact, the minute that you write Poynting vector as E cross H, and I'm shocked, surprised that many people say this with a straight face without recognizing this. The minute that you say the Poynting vector is E cross H, you are saying that Maxwell's microscopic equations are not good enough. Because if you stick with this formula, that everything is reducible to bound charge and bound current, then you can derive Poynting theorem. There's only one way to derive Poynting theorem at that point. And then you find that the Poynting vector should be E cross B, not E cross H. So anyone who says the Poynting vector is E cross H, and you can count Landau and Lifshitz among them, you can count Jackson among them, and many, many other people, they are automatically saying, by default, that Maxwell's microscopic equations are not good enough. But still, people say that without realizing the inconsistency of that statement. So once you do that, they say you eliminate D and H, everything is written in terms of E and B. And then they say, therefore, everything is reduced to the microscopic equations. And I have argued in this talk that this is wrong and you should not do that. And of course, they add insult to injury and they say that only engineers care about D and H. Physicists who are, several levels above the engineers, they always work with E and B. But that is just a statement about physicists rather than about electromagnetic theory. I have already mentioned this in the previous slide, and I have also said this several times. Is the Lorentz law complete? And the answer is yes. It includes everything because you have to reduce everything to bound charge and current before you can use the Lorentz law. But it is not consistent with Maxwell's equations, with relativity, and with the conservation laws. And that's why we need this modified form of the Lorentz law, which I call it the Einstein and Loeb equation. So this is the alternative formulation of the Lorentz force on the electric dipole. This is the conventional form of the Lorentz force with rho being minus dp. This is the Einstein and Loeb form. You have P del E here rather than del PE. The second term is the same. With magnetic materials, if you use the Lorentz law, your bound charge is 0, your bound current is given here, and therefore the Lorentz law gives you this for the force. But I have argued that that's not correct, and the correct formula is the Einstein and Loeb. For the magnetic dipoles, the H field, the gradient of the H field exerts a force on the magnetic dipole, and the E field exerts a force on time-varying magnetic dipoles. And the correct formula for the force on the magnetic dipoles is given here. So I have taken a lot more time than I was allotted, but I apologize. Here are my conclusions. Maxwell's macroscopic equations are exact and self-consistent. They are also superior to microscopic equations. The Lorentz law of force is incompatible with the special relativity and with the conservation laws. The correct force law is the Einstein law. Electromagnetic energy is given by the Poynting vector, and that's a postulate. That's not something that you derive from the Maxwell's equations. Momentum density is Abraham momentum density given by Poynting vector over c squared. And finally, the postulates are complete, consistent with relativity, with conservation laws of energy, momentum, and angular momentum. Thank you very much for your attention.
So we had a lot of questions during the talk, but I'm wondering if there are any who have further questions or comments.
I have a lot of questions.
Yes.
I discussed it outside.
Yes, I have a question, but
Yeah.
in general, I mean, I just want to get your opinion.
Yes.
What is your opinion about the connection between Maxwell's theory and quantum mechanics? I mean, obviously, of course, they're separate issues.
Yes.
But as we get more and more into the nanostructure,
Yes.
this becomes a necessity. Is there any good way to do it? I mean, there are different ways, but in your opinion, you're so familiar with this.
Yeah.
I'm interested in this.
Well, the first part of this talk, I talked about Doppler shift. And I said that the energy of the photons is h bar omega. That's quantum optics. That's not Maxwell's theory. And at least I know that if I use Doppler shift to derive the radiation pressure, I get exactly the same formula as I get with the Lorentz or generalized Lorentz law of force. So in that context, things are consistent. The other point is that a magnetic dipole is not a loop of current. If you go by this idea that replace P and M with charge and current, that current in the kernel of M, in the case of the magnetic dipole, is just a loop of current, the Amperian loop. That's what Ampere initially proposed in the 1820s. So a loop of current producing a magnetic dipole produces problems. As Shockley discovered, there's going to be hidden momentum in that case. But I think that's consistent with quantum mechanics, because a magnetic dipole is not just a loop of current. A loop of current would be easily disturbed. If I put an electric field that has a gradient over a loop of current, E dot J is the rate of exchange of energy. So energy is going to be given or taken away from the current by the electric field. But can you imagine a single electron or a single neutron which has a spin, and therefore it has magnetic dipole moment, being affected by such an electric field? So you have an electron sitting here, and you put a magnetic field along the spin axis and make that magnetic field increase with time. As a result of that, you have created a loop of electric field around the loop. So you're constantly giving energy to this thing. Does the spin go up? Can you imagine putting an electron in a time-varying magnetic field and then seeing its spin increase? Spin is a quantum mechanical entity, and it's characteristic of the electron. It's characteristic of the neutron. You cannot get it to change like that. And that, again, points to the essential nature of the magnetic dipole. You cannot think of magnetic dipole as a current loop, as an Amperian current loop. It's a quantum mechanical object, and you have to treat it the way Einstein and Lop do, as just an entity on its own. Don't think about what is inside it. Here's the expression for force. Here's the expression for torque. I don't care what's inside it. That's the scaffolding. I don't need that. Give me the equations. I can tell you what the force is. If that force happens to be consistent with the conservation laws of special relativity, it should be okay. The same thing goes with the electric dipoles. An electric dipole is not just a pair of charges on a stick or on a spring that you can pull apart or bring together. An electric dipole is an electron going around the nucleus. with slight displacement. But that's a quantum mechanical entity. It's Schrodinger equation that tells us what the distribution of the wave function of the electron should be. And so that electric dipole should not just be treated as a pair of ordinary charges on a stick. And again, Einstein and Loeb tell us that, yes, an electric dipole has its own identity. It is P del E. Remember this formula? If you go by the classical interpretation, minus del P is the charge distribution. This is the force on the electric dipole. So that electric part of it is minus del P E. But Einstein tells us it's P del E. In other words, each dipole has its own identity. Locally, it responds to the gradient of the electric field. And therefore, the quantum mechanical nature of the dipole matters. It comes into play here. Otherwise, it would be this formula. So, to the extent that these things are consistent with conservation laws, I think they are a better representation of classical world and more consistent with quantum mechanics than the traditional way.
That's an excellent point.
Yeah.
Because that would be a really nice connection. That if its argument is slightly further.
Yes.
So, for example, you mentioned the P and M, and I like the way you described it, that you should not look at it as a group of current and so on. But the electric field and magnetic field are still classical. What would be the next step in order to make P and H also quantum entity? In other words, we go into quantum optics.
Well, we have quantum optics, right? We have the A and A dagger, the rising and the lowering operators, and that's how the fields are described in quantum mechanics. And there are some new things that you get from quantum optics that you don't get from classical optics, like two photons going through a beam splitter, correlations, things like that. Entanglement. You don't get that from classical. But that's okay. All I'm saying is that within the realm of classical electrodynamics, you have to be self-consistent. You can't just have hidden momentum. You can't violate the laws of special relativity. And these 9 rules that I wrote down, 4 Maxwell's equations, pointing vector, Abraham momentum, angular momentum, etc. These 9 rules are a complete and consistent set of rules within the classical realm. As soon as you go to the quantum realm and you have entanglement and things like that, then you have new phenomena. But at least these rules are not inconsistent among themselves and with the conservation laws and with special relativity. Yes.
Slide 12 is supposed to receive.
Slide 12.
We have this expression for the square.
Yes.
Is n corresponding to some dielectric?
You mean here
Yeah, there.
and here? Yes.
What you have instead of a plasma,
Yes.
the refractive index would be less than
Yes.
so is some change or just apply this expression? It doesn't have a change of sign.
No, actually, I don't know if n is less than 1. I haven't thought about that. I have thought about negative index media, metamaterials which have negative index. And the formula also works for negative index media. And no, not complex, but negative. N is negative, so both mu and epsilon are negative. Because there are papers recently in Nature Materials, where they say that according to Veselago, that there should be a reversal of the Doppler shift when light is reflected from a negative index mirror, or when you have a negative index mirror behind the a mirror behind the negative index material, and then light that gets reflected from that will be Doppler shifted in the opposite direction. And not only did Veselago say that, but recently a group from Shanghai experimentally verified that. So they did an experiment and they showed that the Doppler shift goes the other way. The mirror is going backward and the Doppler shifted light is blue. So the light is blue shift rather than the red shift. And first of all, I don't know who these referees are and how do they accept such papers. Even without doing any analysis, I can say that that's wrong, because both energy, not only is energy conservation violated, but also momentum conservation is violated. If I don't even know what the negative index is, you just tell me that you have a mirror with some dielectric in front of it or not. A photon shines on it and comes back and is blue shifted, and the mirror is going the other way. I say BS, which means, in polite language, it means nonsense. You can't do that. It's just violation of energy and momentum. Just because you wrote a lot of complicated equations and you referred to some authority and you said Veselago already predicted that in the 1960s, that doesn't make it any more valid. It's nonsense. Pure, unadulterated nonsense. And of course, I can do the analysis here and put negative index and see that it comes out the way it should be, redshifted. But just by looking at conservation laws, you can see that that's wrong. And I know why the experimental result came out wrong, by the way, but that's a different story.
I can follow up on that. Supposing n is not the pure number, positive or negative, but is indeed complex.
Yeah.
What happens then?
Well, then we have something else to worry about, because yeah, because the idea here was that we are not giving any energy to the material medium.
Yeah. I was thinking in terms of
Well, we're going back.
you never have a perfect mirror.
Yeah,
This is great for thought experiment.
sure. No, we can take that into account, but then we have to see how much of the energy has gone into the dielectric and how much of it has gone to the mirror. When I wrote the conservation of energy equation, I assumed that no energy is going to the dielectric. It's all going to the mirror. So conceptually, I can do that, because everything can be done in the limit. You have the Kramer's Kronig relations that tells you that you always have to have negative part for the epsilon, imaginary part for the epsilon. But it doesn't tell you that you have to have a large amount of imaginary part. You can go as far away from resonance as you want, and then you can push the absorption to the limit of essentially negligible. But yeah, if you want to include absorption, then you have to think about it, and even also dispersion. If n is less than 1, dispersion comes in. Then you have to write the conservation laws accordingly. But I'm just using a simple case where it's easy to analyze, and I tell you what the result is.
Anybody wants to say something, I'm sure that we have to entertain questions.
Yes. Thank you very much.